Hi guys, in this video we will look at the FriedelCrafts reactions, and we will begin with the alkylation. And of course, as the name implies, we'll be putting an alkyl group onto the aromatic ring. Here's our outline. We have a dedicated handout for the FriedelCrafts reactions. Now in the alkylation, our electrophile is going to be a good old-fashioned carbocation. And here's an example of a FriedelCrafts alkylation reaction. Benzene will react with isopropyl chloride, or more in terms of an IUPAC name, 2-chloropropane. Yeah. In the presence of a Lewis acid catalyst. All right. Now we used aluminum trichloride or aluminum tribromide as a Lewis acid catalyst for chlorination or bromination of the ring. So we saw that a little bit earlier. And in this reaction, the isopropyl group will end up being bonded to the ring. And that is, of course, an alkyl group, so it is an alkylation reaction. And if we completely balance this, we'll form HCl. Now we made this carbon-carbon bond here. Of course, that's what an alkylation reaction, well, not always, it could be an N-alkylation, but this is a C-alkylation. Basically, this does allow for carbon-carbon bond formation. This reaction, by the way, was first described in 1877 by the two chemists Friedel and Crafts. And it is one of the probably the top 10 reactions in organic chemistry. All right, let's look at the mechanism for this reaction. First step is the halogen here complexes, these electrons complex with the aluminum. The aluminum has empty d orbitals. It also has an empty p orbital if we consider it sp2 hybridized. That would lead to this here. Now at this point, this positive chlorine, okay, and that's the purpose of the Lewis acid. After complexing, it makes the chlorine positive. All right, we typically don't protonate a halogen with H+, but we can make the chlorine positive by complexing with a Lewis acid. We saw this when we did a chlorination reaction or bromination reaction. This could have been Cl2, but the halogen complexed with the iron. Okay, halogen became plus. The iron with an additional bond became negative. But now the bromine became partial positive. The ring attacked the partial positive. All right. Well, the carbon becomes partial positive here because of a dipole, but because it's a carbon and carbocations can be formed, readily formed, this chlorine can just leave. These electrons move on to chlorine, and that would give that carbocation plus aluminum with 4 chlorines bonded to it. The aluminum is minus. So this is another way to make carbocations. Complexing a halogen and then the complexed positive halogen, then leaving, ionizing off to make the carbocation, Now the ring, all right, and if we had bonds drawn in more precisely, these electrons can swing up and attack the carbocation. Up and attack that carbocation. We just made that bond right there, yeah. There's an H there, of course. This becomes the cation in the ring. And there you go. There's your sigma complex that occurs during our EAS mechanism. This is just a standard EAS where instead of the electrophile being a generic E+, we showed back at the very beginning, we have actually a carbon plus, a carbocation. Resonance stabilized. Now something needs to take the H, put the electrons back in. I should have drawn this out. Full structure, aluminum, Cl, 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 Cl minus. The aluminum is now not happy. It has too many electrons around it. It does have an octet, but it's a negative charge. Tells the chlorine, hey chlorine, you and your bonding pair take a hike. These electrons break away from the aluminum and go bond to H. These electrons move in to make pi bond, and that gives those two products, HCl there, but we also reform aluminum trichloride, which was our catalyst. And now it can come over and complex with another molecule, the alkyl chloride, and proceed again. FriedelCrafts Alkylation. Now this reaction works with primary, secondary, or tertiary sp3 halides. All right, we used a secondary halide here. Now we made a secondary carbocation. Now if you think about it, it works with primary halides. You're going to make a primary carbocation. Well, it's a little bit suspect there. I'm not going to show it or get into it, but some organic chemists don't really believe it's a primary carbocation, but instead we attack a partial positive carbon where the halogen didn't leave to make a formal carbocation. Okay. I will typically avoid showing anything like this. Secondary, tertiary, of course, are easier carbocations to form. All right. Now, typically, theoretically, your halogen can be bromine or iodine, but chlorine is the most common because it works well and it's cheapest, and it's just thus the most common. Now, this reaction does not work with sp2 or sp halides, because an sp2 or sp original carbon is not going to want to form a carbocation. So you're not going to be able to use chlorides like this, chlorobenzene, or this alkene, chloroalkene. Okay? I am talking about as electrophile. I am talking about this species. When I show chlorobenzene, that doesn't mean you can't have chlorobenzene here and it react with the same compound. All right? Now, there are other routes to carbocations. The most common route that we know of maybe is to take an alcohol, react with H+, We can protonate and then water leaves to make a carbocation, right? That's best with tertiary alcohols. It's also quite common to use BF3 with an alcohol. And BF3 would be a Lewis acid, not a proton acid. And these electrons complex with the boron, and we get something that looks like because the boron has an empty p orbital. All right. Then the looks like a protonated oxygen, but instead of adding another proton, we got to this point by complexing with the boron, but this leaves, and that would give you your carbocation, and then a boron negative with these 4 groups on it. All right. That's shown condensed. But in practice, it's actually common to use BF3. It tends to work a little bit better than just a proton acid. Now we can also get carbocations, as you should remember from Organic 1, from alkenes, right? So alkene would react with H+, electrons this way to make, all right, same carbocation we made above. And of course the benzene ring above would react with this same thing. So we could show a reaction, alternative synthesis above. We start with benzene. We can get to that product by reacting with that alkene and sulfuric acid. And so we would expect these to react just like down here to make the carbocation, and then the ring could attack the carbocation. So basically the mechanism is the same, it's just different ways to make carbocations, and I think this is a new way for us. Complexing an alkyl halide, okay, alkyl halide, an sp3 halide, with a Lewis acid. Aluminum trichloride is the most common. Occasionally you will see tin tetrachloride used as a Lewis acid. So sometimes, but most common at the introductory level is the aluminum trichloride. Okay, FriedelCrafts Alkylation. And that's shown on our outline here, where essentially we're replacing an H with an R group, right? And in this reaction, we replaced an H on the benzene ring with an isopropyl group. Now, there are some limitations or potential problems with the FriedelCrafts alkylation. One is, it fails when you have strongly deactivating subs on the benzene ring. Now, your strongly deactivating subs, that is group 4, are also known as metadirectors, right? So sometimes you could say it fails with a metadirector on the ring. So if you tried to react nitrobenzene with the same reagents as the previous page, you would actually get no reaction. No reaction would occur. Nitrobenzene doesn't undergo FriedelCrafts alkylation. Now because of that, nitrobenzene is sometimes used as a solvent for FriedelCrafts reactions, because it is a solvent that's occasionally used in the lab. And one time where it may be more common to use this is in a FriedelCrafts reaction, because it doesn't react. Okay, number 2. The FriedelCrafts reaction or alkylation fails with anilines. Okay? Doesn't work if you try to react it with an aniline. Now why? Well, it's a reactive ring. All right. And by the way, why does nitrobenzene not react? Yes, it's a deactivating sub. Okay. By the way, you can do other EAS reactions with nitrobenzene. For example, you can react these with maybe bromine and FeBr3, and we would expect to get metabromination. That's an EAS reaction. This is an EAS reaction. Why does it not work with FriedelCrafts type reagents? Well, it's hard to say, but it must mean that the transition state energy of this attacking a carbocation is higher than the transition state of nitrobenzene attacking a complexed bromine here. I mean, that's kind of obvious if one reaction works and the one reaction doesn't. But then we could say, well, why are the transition state energies different? And that gets into, well, it's not easy to explain, but we do know that if you go to lab, this reaction will work with nitrobenzene, but a FriedelCrafts reaction will not. Apparently the ring is not activated enough or reactive enough. Now with aniline, it should be, this is a group 1, this is a strong donator, this should be an activated ring. So why does the reaction fail with anilines? Well, that's because the amino lone pair is a pretty good base. All right, you could make an argument there, but it will complex with the aluminum. And when it does, the nitrogen becomes positive, and now the nitrogen group is no longer a group 1, but it has become a group 4 strongly deactivating group. And if you remember, we mentioned this over here. Amino groups are activating, but in the presence of proton acid or Lewis acid, these can be converted to positive nitrogens, and they are now strongly deactivating. And at that point, we refer to group 1. The reaction fails with strongly deactivating subs. All right, and so that's why these reactions fail with anilines. Now note, the FriedelCrafts reactions do work with amides. Like this, because here the lone pair we rationalize based on the fact that anilines don't react with these do. This lone pair must not complex with the Lewis acid as much or at all. And we do expect this lone pair to be less basic because it's delocalized not only into the ring but also into the carbonyl. Now FriedelCrafts reactions do work with oxygen substituents such as phenols or anisols. All right. So really, any other group other than a strongly deactivating substituent or an aniline, an amino group, other groups on the ring still will react. Okay, number 3. The other limitation or problem with the FriedelCrafts alkylation is rearrangements. If you try to react benzene with 1-chlorobutane with a Lewis acid, trying to make compound A, you will actually get more of this product. Now the mechanism here must be this complexes with the Lewis acid. Now I'm going to cringe here, but to me the only way we can get a rearrangement is if we show a carbocation, and I'm going to do that, but we'll see that that leads to a primary carbocation plus our negative aluminum with 4 chlorines. Now, I've always said let's avoid making primary carbocations, but I don't know we have to in this instance. Now, the ring could attack the primary carbocation. That's how you would get compound A. So how do we get the next compound? Well, we have 2 H's here, and what would we expect this carbocation to do? Hydride shift. Alright, and I'm not going to draw in these H's again, but we see that one of them moved over here. That carbon now has 3 H's, this carbon now only has 1, and now we have a secondary carbocation. And so now the ring could attack here, give our sigma complex, and then when we lose the H to restore the aromaticity, we would have this rearranged product. And that is the major product here. So if you were trying to make compound A by this reaction, you would actually get another product in higher yield. And thus we would say the rearrangement was a problem. Now if you wanted this rearranged product, that wouldn't be a problem. It'd be a good thing, right? So maybe a problem or not, in the end we do need to always look out for a rearrangement of our carbocations anytime we're forming them and reacting them. Okay, the next problem with the FriedelCrafts alkylation is polyalkylation. Now even though over here I showed this reaction giving this product, I did not talk about the yield. This reaction is prone to continuing again and putting a second isopropyl group on the ring. And that's what I show here. Once we put one isopropyl on, all right, this could then react again with the carbocation. Now, of course, this is an ortho pair director. And so we would expect the next reaction to put the electrophile ortho or para. Now I'm only showing the para product here, could get ortho. Although with FriedelCrafts reactions, para products tend to be favored a little bit more than ortho. And then we could react again. And then we're going to put ortho next to one of these groups. That's the only position open. And we can keep going until we really put 6 groups on here, if possible. Now, as we add more and more groups, it becomes sterically congested, and it's harder to get one maybe in between 2 existing groups. Okay, now you don't need 3 equivalents to get here, because think about it, as soon as one of these reactions takes place and this is now in the mix, all right, and back over here, you're making more of these. Once these start forming, you can't tell it to, okay, I want you to forget about this carbocation, I only want benzene to react. Think about it. Which is more reactive towards EAS, benzene or isopropylbenzene? This is an activating group. The product is more reactive towards the carbocation than the starting benzene. So the product will compete with the carbocation and it will actually win out. And so before this reaction is complete, your product will start reacting and you'll start putting two groups on. Now, with two groups, this molecule is doubly activated for EAS. So it will start reacting with the carbocation instead of benzene. So before you know it, benzene will be like, hold on, I want to react. But these guys over here will say, sorry, we're reacting. And they'll just keep on going. And you'll end up with multiple alkyl groups on your ring, and we call that polyalkylation. All right? That's a common problem with alkylation. Now let's move to FriedelCrafts acylation. Now acylation we'll see gives aromatic ketones. And here, instead of using an alkyl chloride, we use an acyl chloride. All right. Now an acyl group is a carbonyl group with a carbon bonded to it. That's the generic term for such a group. And that's the type of group we're adding to the ring. And so it's called acylation. Now these acyl chlorides are sometimes also known as acid chlorides. And if you look on your functional group list from Organic 1, we probably called them acid chlorides at the time. That's because these are commonly made from carboxylic acids. We will see that chemistry during test 3. Okay. The mechanism is pretty darn similar. This chlorine, similar to the alkylation, complexes with your Lewis acid. The positive chlorine then acts as a leaving group to give this weird looking carbocation. It's the carbon is the carbon of a carbonyl. Where have we seen such a structure before? Where the carbonyl carbon is positive. First off, it's called an acylium ion. Okay? It's like the acyl group is a carbocation, acylium. Do you remember where we've seen these before in Organic 1? We saw these in mass spec. Acylium ions are formed in the mass spec of carbonyl compounds. Here we're forming an acylium ion in a reaction mechanism. Now it's resonance stabilized, okay? These electrons can move here and we get a resonance structure that looks like this here. Now actually it's linear. Actually right here it's linear because that carbon, having just two regions around it, is sp linear. So really it's drawn wrong here. I just drew it like this because that's how it was drawn originally here. See, here it's sp2 trigonal planar. When that leaves, it does become linear. Of course, the true structure is a blend, and all resonance structures have the same hybridization because it's really just one structure. So, of course, this is your major resonance structure because you have more bonds here. All right, but I will still typically react the acylium ion. Now, if you've got a aromatic, these electrons can attack the acylium carbon plus, and that gives a bond here. We just made this bond. There is an H here. There's be a carbocation here, bonds here, right? Then one of these chlorides leaves. The aluminum says take a height, take your bonding pair with you, and it comes over here, it makes bond to H. These electrons are going to move here, right? And it's now the benzene ring with an acyl group. That's what we have here. We'd form HCl, and we'd also reform our Lewis acid. Same mechanism as the alkylation, except here we attack an acylium ion. Now, the acylium ion is not going to rearrange. Because it's resonance stabilized. And so while the alkylation is prone to rearranging, because in the alkylation you make just plain old carbocations that typically are not resonance stabilized, when you do an acylation, you're making a resonance stabilized acylium and it does not rearrange. So we solve one of those problems. By the way, you can always work with any resonance structure. I could have reacted my benzene ring with this resonance structure. These electrons attack the carbon and move these here. That gives the same intermediate, right? You can always work with any resonance structure because neither one is actually correct. The true structure, of course, is the resonance hybrid. Here's an example. We take benzene with this acid chloride, aluminum trichloride. We'd expect to get this product. Yeah? You need to make sure you see that. Okay, you're going to make that acylium ion. The ring will attack it. Okay. Now we will not get any polyacylation. That's because here we're putting on a deactivating group. It's actually a strong deactivator. And what do we know about strong deactivators in FriedelCrafts reactions? They fail with strongly deactivating substituents. Okay? This applies to acylation as well. All right? this is not going to do another FriedelCrafts reaction. And so it doesn't compete with the acylium ion, only the benzene reacts with the acylium ion. Isn't that wonderful? Now, a common reaction of these aryl ketones like this is we can remove the oxygen, deoxygenation, and we can turn this into a plain alkyl group. This is 4 carbons. Okay. We can remove the oxygen on the benzylic carbon. Remains 4 carbons, but the carbon bonded to the ring no longer has a oxygen. It's no longer a carbonyl. We replace the oxygen with 2 H's. All right. This, of course, would be a reduction. We can reduce off the carbonyl oxygen. We'll talk about the reagents here. But this is actually a 2-step synthesis of compound A over here, where if we tried to make compound A by a direct alkylation, we would get a low yield for the reason we explained. But if you try to make compound A by a 2-step route, that involves FriedelCrafts acylation first, followed by a carbonyl reduction, removing the oxygen, we get a much better yield of that A product, of an alkyl product. And typically, if you ever want to put on an alkyl group, it's best to do a 2-step route. Because making the aryl ketone, you avoid polyacylation. Okay. You also avoid rearrangements. Now, reagents that will remove this oxygen include, first off, hydrogen gas will do it. This will reduce alkenes, alkynes. It'll reduce nitro groups to amino groups. It will also deoxygenate aryl ketones and replace the oxygen with 2 H's. We're not going to look at any mechanism for there. A more classical textbook approach is the Clemmensen reduction. This uses zinc and mercury amalgam and HCl. Sort of like a dissolving metal reduction. All of these, this is a reduction, of course. And this is the classical textbook approach. A third way is the Wolff-Kishner reduction. That uses hydrazine, okay? Under basic conditions. We'll actually look at this mechanism during test 4 when we look at the chemistry of aldehydes and ketones. We will not look at it right now. Fairly common textbook approach. So 3 different ways to deoxygenate these from the acyl group to the alkyl group. Now, a note here, you can make aldehydes this way, okay? But this compound is not stable, all right? You might theorize that you can take this, complex it with the aluminum, this leaves, okay, just like above. And if the ring attacked here, you'd end up with an aldehyde on the ring. All right, you can do that. This chemistry certainly makes sense. The problem is this acyl chloride, is it really an acyl group with an H here? I'm not sure, but this molecule is not stable. The reason I point this out is because sometimes students will try to use this to make aldehydes on the ring. But there's actually a tricky way to do this. You can use carbon monoxide and HCl, mix these two together, because these react to produce this molecule in situ, that is, in the reaction. Now that's actually an interesting mechanism. If you take that and react it with HCl, how can you show this product? It's actually pretty straightforward, and this is an equilibrium. This acts as a base, yeah, and then you get H here. It's going to look so simple once we do it. Cl minus, right? Form right there. That's just protonation of this. Now these electrons come here, kick these over. You do have a strong dipole here. What does that give? All right. Well, there you go. There's your product. So there's your straightforward mechanism. Isn't organic chemistry wonderful? Isn't mechanistic thinking wonderful? How you can just see how this flows so nicely to give this product? Okay. FriedelCrafts Alkylation. Here are some predict the products for homework. I'll let you do these on your own. See what type of questions come up. The second one here, I give you a hint to think intramolecular, because it's really just one molecule. Then down here we have an alcohol with acid, alkene with acid. What type of electrophiles can we form here? All right, some think about there. This shows an application where FriedelCrafts chemistry is used. It's a synthesis of Tazarac, a compound or a drug used to treat acne. If you look at going from 16 to 17 here, okay, it's really a FriedelCrafts alkylation. And it's really just H+. Okay? Now this is aqueous. The P2O5 actually reacts with some water here to form more phosphoric acid, so it serves to make this even more concentrated than 85%. What is phenyl H? Well, that's a benzene ring and the substituent is H. I mean, that's just benzene. That's an abbreviation of benzene there. Of course, if I did phenyl chloride, that would be a benzene ring with a chlorine. This is a benzene ring with an H, okay? It's a common abbreviation for benzene. So really it's just H plus here. Benzene's the solvent, but hopefully you can imagine how you can get to here. But then the next step is also a FriedelCrafts, but this is an acylation. using this acyl chloride. And here they're using the tin tetrachloride. If you remember, I told you it's sometimes used instead of aluminum trichloride. So it's the Lewis acid. See the acyl group. One thing to think about for 17 is the starting material. What's going to be the directing effects here? Which will direct, the sulfur or this carbon group? Think about that. All right. Most of the other chemistry here, well, the first reaction is just a good old SN2 to make this bond here. The only other chemistry you would recognize here is the N-butyl lithium. There's an H here. The N-butyl lithium, the base takes this H. If you remember, the hydrogens of terminal alkynes have some acidity. And that leads to the acetylide anion. Then it reacts with the zinc and displaces one of the chlorines to sort of get this. Then they do a palladium catalyzed reaction. But that's probably the only other chemistry here that you would recognize at this point. Okay, but it is a couple of examples of FriedelCrafts reactions. You can also take a look at this page. A synthesis of Vioxx. It used to be a drug used to treat arthritis until it was pulled due to some heart-related side effects. It was a very big selling drug, made lots of money. The first step here is a FriedelCrafts acylation. Actually, the other reactions, two of the others we'll see during test 4. And this one here is just a good old-fashioned SN2, where these electrons kick that bromine off, yeah, and made this bond here. So FriedelCrafts, test 4 chemistry, we'll see later. This is an oxidation of the sulfur, which is possible. Using hydrogen peroxide. So lots of applications of FriedelCrafts reactions. That's why it's one of the top 10 reactions in organic chemistry. Of course, there's about 20 top 10 reactions. One of the others we've seen so far, probably the Williamson ether synthesis. Okay, please be working on these, see what type of questions come up. Also reading in your textbook and problems in the workbook. FriedelCrafts reactions.